When you prompt a modern large language model, the end product appears as a seamless, rapidly generated stream of coherent text. It looks like cognition, but neural networks possess no understanding of syntax, vocabulary, or poetry. They are mathematical structures that accept numbers as inputs and output other numbers. No exceptions. There is a massive conceptual gap between a simple arithmetic equation on a chalkboard and the architecture required for generative AI text prediction. That gap is bridged entirely by scaling up basic operations. If you know how to add and multiply two numbers, you possess the requisite mathematical knowledge to understand how these systems operate. We are going to build a large language model from scratch, starting with single numbers on a piece of paper and ending with the complete transformer architecture. To understand artificial intelligence, we have to strip away the mystique of machine intelligence and expose the pure mechanical arithmetic underneath. Before we can generate human language, we need to establish a baseline feed-forward neural network using simple scalars, single numbers. We start with a basic classification problem, identifying an object as a leaf or a flower, using exactly two numerical inputs, its RGB color value and its volume. This diagram illustrates the core mathematical equation of a single neuron. We take our input data, pass it along a connection line, and multiply it by a predetermined weight. Those products collect inside a node, where they are summed together, along with an additional constant number called a bias. The math yields raw numbers at the end of the network. We assign human interpretation to those results. Here, we decide that whichever node outputs the higher number dictates the classification label. If the top node is higher, we call it a leaf. When the network is first built, the weights are random, so the output is likely wrong. To fix this, we measure the mathematical difference between the network's current output number and the precise target number we actually want. We call this difference the loss. Once we calculate the loss, we systematically tweak each weight by a tiny fraction to see which direction decreases that error. We move the parameters slightly down the slope of the error curve. This mechanical adjustment is called gradient descent. This specific process, calculate loss, adjust weights slightly, recalculate, loops millions of times, continuously optimizing the parameters. Learning in this context involves no cognitive deduction. It is strictly the mechanical minimization of mathematical error through repeated scalar arithmetic. Translating this structure to language generation requires a leap in how we represent data. A simple numerical sequence where A equals 1 and B equals 2 fails to capture the semantic relationships necessary to distinguish words. Instead of single letters or full words, the input text is chunked into smaller, recognizable pieces called sub-word tokens. A word like cats is broken into the tokens cat and s. We then map each token by upgrading from a single scalar number to a vector. An embedding vector is simply an ordered collection of multiple numbers, pulled from a predefined matrix, assigned to represent a specific token. These embedding vectors act as trainable parameters, shifting and optimizing during gradient descent, just like the weights in our scalar network. By treating the input representations as trainable, the training loops naturally force tokens that appear in similar contexts to end up with mathematically similar vectors. They group closer together in the data. To accept these vectors, the input layer of the neural network expands drastically. Instead of a few single nodes, it grows wide enough to process these massive arrays of numbers simultaneously. Semantic meaning and linguistic context do not exist in the machine. They are encoded purely as calculable geometric proximity in high-dimensional vector space. In a standard feed-forward network, the weights connecting different positions are static. Because these weights never change, the network lacks a way to adapt the importance of a word based on where it appears in a sentence. If we use the sentence, "The girl wrote in her will," the word her depends entirely on the word girl appearing earlier. To capture this, we need weights that are functions of the words themselves, calculated dynamically for every new sequence. This dynamic calculation is called self-attention. It creates a new, contextual vector by taking a weighted sum of all previous words in the sequence. To determine these weights, we transform each word embedding into two distinct roles. We create a key vector that describes what information a word contains, and a query vector that represents what information the current word is looking for. This allows the model to compare every word to every other word to find a match. The network then performs a dot product on these two vectors. It multiplies the corresponding values of the key and query and sums the results together. The resulting scalar is a precise relevance score. It dictates exactly how much attention the current word should direct back to that specific past word. The ability of an AI to understand context and grammatical structure is achieved strictly through matrix dot products calculating these relevance scores on the fly. This chart visualizes a critical flaw with dot product outputs. The operations yield raw, unbounded numbers, known as logits, that can skew into extreme positive or deep negative values. A neural network cannot be reliably trained to minimize error when its target bounds are infinite. You cannot have a negative percentage chance of selecting a word. To fix this, a mathematical filter called the Softmax function is applied to the final output layer to normalize these wild numbers. Softmax forces every raw number in the array into a strict probability distribution. It ensures every value is positive, and more importantly, that the entire set of numbers adds up to exactly 1.0. With a normalized distribution capped between 0 and 1, the model can safely assign a valid percentage chance to every potential word in its vocabulary. The Softmax function translates volatile arithmetic into a stable, constrained system that can reliably generate text one token at a time. We now have all the necessary mathematical components: trainable vector embeddings, dynamic dot product attention, and normalized probabilities. This animated diagram shows how these parts assemble into the final GPT architecture. The sequence is rigid. Input text converts to vector matrices. Relevance is computed via attention dot products. Layers are normalized, and outputs collapse into probabilities through Softmax. Llama 3, GPT-4, and every other major model utilize this exact block structure, repeated dozens of times across billions of parameters. The sheer scale of the computation requires massive data centers, yet the mathematical rules driving the entire system remain strictly confined to addition and multiplication. The resulting text feels remarkably human, but the intelligence is an illusion, constructed entirely by billions of foundational mathematical operations perfectly stacked together.